Okay, great. I'm recording now. Just to kick off the recording, welcome all. Today's topic for Microsoft Networking Academy is high availability for network virtual appliances. And we're going to be talking a lot about design with the Azure Load Balancer today and talking a lot about VNet design, which is part and parcel of this. So welcome. Happy Friday. I will then pull up the whiteboard and we will begin. I had planned, of course, great lab work for this. Due to a couple of circumstances, workflow circumstances, lab complexity circumstances, I wasn't able to execute on the lab. I apologize for that. I think there's ample opportunity to revisit any of these topics with the lab. In some way, we're going to cover so much ground today, it really is better to have a separate lab breakout because we're going to go backwards in time and understand a little bit about Azure's history as an underlay in an infrastructure system to arrive at our understanding of how and why we're designing with the Azure Load Balancer today and why this is a good choice. So this is where our journey begins. What I have in front of us is a very simple, rough representation of what's happening in Azure. This is in terms of an underlay, in terms of the actual data center physical fabric that has been built at massive scale. We would call this hyperscale at a global level in order to sustain a vast multi-tenant, sophisticated platform capability and to make this infrastructure fungible and flexible and scalable, and to make this infrastructure extremely robust, so we have very, very high uptime, and also to make it cost efficient, meaning that if we designed this underlay in different ways, we create points of inflection on cost that we don't want, because we want cloud to be affordable and economical for our customers, so we can pass cost savings in the platform on to our end users. Because let's face it, we're running a business. The more our infrastructure costs us, the more we have to, in part, defray that cost with the cost of the platform, and nobody wants that. We want this platform to be as economical and efficient as possible. So in order to understand why I'm going to talk about this, I should first talk a little bit about my relationship to this ecosystem. I have been involved in Microsoft's infrastructure in one way or another for quite a long time, going back 10 years. First as a vendor that faced Microsoft and helped them with a couple of different appliances in this fabric, supporting them from a vendor standpoint and helping them resolve design challenges. And then as a Microsoft employee in the flesh, working in our infrastructure department as a load balancing architect to make this fabric come together and work. So I've kind of seen it from both sides. Let's talk a little bit about how we ended up with this. In Azure, this mechanism that we're looking before us is called a clause fabric. To some, that is not a mystery. A clause fabric is a well-known way of designing big routing infrastructures today. It's comprised of a couple of tiers. We have here on the left a border. Let me change my marker. A spine, and the spine can be in levels deep. So in this diagram, we see a second level of the spine and a leaf. What are the advantages of designing an infrastructure this way? One is you get really good packet distribution, assuming that you scale these tiers out correctly to make sure that they are oversubscribed in terms of capacity value. So meaning that this border has been built and scaled appropriately to handle the capacity of any of these given back-end leaf racks and clusters working almost at full force. So if there's n amount of network and compute capacity back here, I'm going to have that same capability in part or whole up at my border. Now, what typically happens in a clause fabric is you can see this interconnected mesh that gets more complex as you go down towards the leaf. Typically, BGP is used in these routing environments because it gives you really good dynamic route distribution and good survivability and path diversity. And another really cool thing that happens is that BGP can take advantage of a neat feature called equal cost multipath, which means for any given destination network that might live stretched out across this leaf. So let's just say an example. Let's just say I have a network 10.1.1.024. If that network is present as a stretch network back here across these various backend leaves, this border will see two equal paths to that those destination networks, right, in the spine level 1. Likewise, if I'm matriculating that down, this first level of my spine will see 4 equal paths to that. And each one of these will also see 4 equal paths. And what I can do is use a very clever algorithm that's available in the industry. It's been around a long time. It's called a rendezvous hash. And a rendezvous hash will look at 5 tuple layer 4 socket information, so source IP, source port, destination IP, destination port, and protocol type, and run it through a mathematical operation that uses that 5 tuple math as an initialization vector to distribute traffic almost perfectly evenly across these different equal paths. So for any packet that comes in, we run a hash against the tuple, and the outcome is roughly 50% of my traffic will come down side A, and roughly 50% of my traffic will come down side B, which gives really good, strong, robust packet distribution, which is what you want. It also solves some really difficult problems with hyperscale that all the big cloud providers want to solve, which is when you're building infrastructure at a global level, it's really, really difficult to rely on layer 2 and ARP and spanning tree and gratuitous ARP to stretch your back-end infrastructure seamlessly across n number of racks or clusters, right? So if you want to logically stretch like a VNet through an SDN stack, and make this available within a region, within a globe. For example, think about global VNet peering. Think about the fact that I can take a VNet in London and connect it seamlessly to a VNet in New York. To make that possible at layer 2 presents a tremendous amount of cost and complexity challenge, meaning that I'm basically having to flood the globe. So if I have a workload here and it wants to participate in the same broadcast domain as a workload here, and I'm using standard networking capabilities to do this, like VLAN tags, and even if I'm embedding my layer 2 frame inside of a layer 3 packet, I'm subject to the mechanics of a layer 2 broadcast domain, which is flood. So the moment I create this virtual machine over here, I need to have some way for the rest of that VNet to discover it. And let's say if that virtual machine is over in London in the UK, and this virtual machine is over in New York over here, if that's what this diagram represents, I have to flood the globe with a broadcast motion in order for this device to essentially become part of my my local broadcast domain. That design simply doesn't scale. It's very expensive. It's very difficult to achieve because if you're flooding the globe, that means your core has to be very big, and it leads to a lot of outages and complexities and problems. So that is why layer 2 is no longer really the muscle that is driving these big data centers. From a cost perspective, a maintenance perspective, an uptime perspective, a scale perspective, it wasn't the right medicine. So we've moved to this Clause Fabric, to this BGP, in order to make this a viable, healthy architecture. Okay, and Microsoft is not alone in this design, right? I think we've done some interesting things that are beyond the scale of this talk that I can't get into to make this architecture really powerful, but Clause Fabric and BGP overlay is something that a lot of big hyperscale companies will do. So think about all your big public clouds, think about all your big social networks. There are deep similarities in some of the fundamentals here in terms of how their data centers are designed. So this is not like a snowflake kind of architecture. Okay, so what is this? Why do I care about this? Why does this even factor in to a conversation about load balancing and high availability? It seems like we're way off in the weeds here. All right, let me pull it in for you and make this make these lines connect. So when we were building this underlay, we obviously needed load balancing, and we needed it in the underlay because we needed good packet distribution from any one host in the leaf to any other host, right? Anytime you're building an underlay, load balancing is a crucial component of this. And so we wrestled with how do we make a load balancing system work. At the time, we were looking at all the Gartner Magic Quadrant load balancing companies that were up to the right. And so all of your big load balancing companies that are market leaders that we all know, we deployed all of them. We have all of them. So I'm not trying to pick on any one company here. I mean, if you know the well established players in the market, Microsoft had vendor relationships with all of them. So we looked at all these different platforms and said, hey, which one's going to be the best fit, or which combination of them are going to be the best fit for this architecture? And we kept running into problem after problem due to where those OEMs were at that time in terms of the design and function of standard load balancing, which standard load balancing does a couple of things that aren't good for clause fabrics and distributed SDN networks. First of all, they put their control plane and their data plane in the same device. So if I'm in a distributed systems, this is very hard to accommodate for, because if I have to scale a device for data plane, I also then have to scale it likewise for control plane. So control plane and data plane are tightly coupled. If I need to scale control plane, I'm also, because the two are bolted together, scaling data plane. I need to be able to divorce these functions into a distributed systems model where I can scale control plane as a factor of X, and I can scale data plane as a factor of Y, so that I have independent motion here. Another problem with this control plane data plane altogether, as we know, which is a very non-SDN kind of way, is that if I have an outage in control plane, it's gonna take down my data plane, right? Because their process is running intimately in the same box and the same hardware, and they're totally tethered. So this led to some problems with uptime, right? If you suffer some kind of critical failure of control plane due to a bug or user error or misconfiguration or memory pressure, your data plane takes a bath. Can't have it. Control plane and data plane have got to be decentralized. Okay, so another problem that comes with the old-fashioned way of load balancing is that it was a scale-up motion, meaning that to add capacity, to add power, to add different and unlock different capabilities, I really would have to stack my load balancer up, which means I'm adding blades, I'm adding line cards, I'm consuming a lot of power out of any one given footprint, and it really starts to make the cost go up. So this is a scale up motion. Because clause fabric is a big distributed system, and what we're trying to do is push compute out laterally left and right here as we scale, we didn't need a scale up motion, we needed a scale out motion. This is called thin and wide. This is good for a couple of reasons. It keeps costs down, it gives you a lot of flexibility on when and where you can scale your data plane strategically for different tenants and different kinds of clusters, and it reduces what we call blast radius. So if I have to put my load balancer right up here or right here, and it's an inline device, remember how I said each one of these tiers in has to be capable for all of the various functionalities in the back-end leaf. This could get very, very large back here. The capacity of these back-end leaf switches, very, very dense. We're talking hundreds and hundreds of terabytes a second. That means that this particular tier, as an inline device, has to scale to meet hundreds of terabytes. Now that's possible using some of these big iron platforms, but if I have an outage on this, and remember my control plane and my data plane are intimately linked, I've lost everything underneath it. The blast radius is massive. So again, we didn't want to approach it from that perspective. So what we did is we decided to build our own load balancer. Now the project that steered this is called Ananta. I'm going to try to write that. Ananta. You can Bing or Google this. There's a great white paper that's written on Ananta that will go very further into what I was discussing today. If you read it and you love it, great. You're insane just like me and you're a load balancing person. Else it's going to be cure for insomnia. But either way, check it out. And it goes into a deeper discussion of what I am talking about today, of why we decided to build our own load balancer to overcome these challenges. So some of the fundamentals of the Azure load balancer are the control plane and the data plane are distributed. We can scale either one of them independently. It uses white box, thin and wide footprint to help keep costs down and scale up. And it uses equal cost multipath and route health injection as a mechanism for good packet distribution through a clause fabric, and it's not inline. So one of the points of inflection is that if we're an inline device, if all of my traffic is coming into this point and it's expecting the response to come back to it, then that means that for all of my outbound connectivity, I have to scale this tier to match that capability. Now, in e-commerce and web and HTTPS-driven world, the vast majority of your content isn't inbound. That's the GET request. Pretty small. Now, for uploading a post, that's different, but for most kind of web-driven standard, e-commerce, there's an app for that kind of ecosystems. Your big throughput requirement is outbound. That's the 200 OK. That's the payload of the HTTP response. That's the file you want, the dynamic content you want, the JPEG you want, the video you want. That's the expensive part. So it was decided that the Azure load balancer from a platform system would be an out-of-band, out-of-line kind of device. So what happens is that, and I can go into this later, this is a very high-level overview, but it will help you understand why the Azure load balancer does what it does, is a packet's going to come in, okay? The Azure load balancer is going to do route health injection for all of the public addresses in Azure from the bottom up. It's the entity that actually does that. So if I have a virtual server that it's a public IP, let's say that it's going to be 16.1.2.3. I don't even know if that's an Azure IP. That's all just an academic example. The entity that actually owns that public address is the data plane, which we call the MUX, of the Azure load balancer. And it's going to inject that via BGP up and up. And as it does, of course, we're going to supernet. So down here, it might be, say, a 24. As it gets up, it might be a 20. And as we get up to our edge up here, where we're facing the internet, and you know, routes need to be smaller and more manageable, so we don't have massive route tables, maybe a 16 or something. So if there's a connection request destined to this public IP address, which is a VIP on my Azure Public Load Balancer, it's going to follow equal cost multipath down. So it's going to come here. Based on the tuple, it might go here, then it might go here, and then it might go here. But the idea is that my backend pool is actually distributed, right, SDN style, across all of these different racks. These are your availability sets. This is how we're able to say, oh, you have a fault domain and you have an upgrade domain. And that's cool because if this cluster or rack needs to go down, you've striped your backend pool across an availability set. That's fine. You're up here, you're up here, you're up here. And the Azure load balancer is going to do equal cost multipath and just distribute this evenly across all this backend stuff, because this VIP 16.1.2.3 lives anycast style on each of these nodes. It's distributed. This is what we call active-active or scale-in. And it works beautifully if you're an out-of-line device, because these tiers are stateless. They never expect a response. The response is going to go around the load balancer out, which means 100% of the capacity of this device from a data plane perspective can be spent handling inbound requests. And then the outbound request can be handled by the big heavy-duty routing iron of the fabric, which is much less expensive to build and manage than a smarter load balancing tier. So it gives us great uptime and cost metrics and stuff. The inbound-outbound motion is handled in part, and I can't get into this, by the SDN stack. That means that we're going to create tunnels on the way in to make sure that we achieve packets going from the underlay into individual tenant VNets and keep it secure and safe, and that the response in terms of the way that the addresses are changed so that the client really sees the VIP on the response is handled by the SDN stack, and that's how that works. Okay, now why did I go through all this trouble? I go through all this trouble to inflect upon how robust and powerful the Azure load balancer is. We found out that this engine, this route health injection engine that we had built, was so robust and so performant. We realized that after we built it, we had exceeded the capacity of any given data center by an order of magnitude of 2. So for kind of throughput and packet requirement coming in to any given data center and region, we realized we had 2 orders of magnitude higher capacity. We had overbuilt this thing, which is a really nice problem to have. So then we said, oh man, let's use this amazing engine for all kinds of cool things. So the Azure Load Balancer is actually the glue that holds a lot of the service chaining together in Azure, both underlay and overlay. So when I have a virtual machine talking to its storage array, like Azure Storage, Azure Load Balancer is involved. When I have a virtual machine talking to its SQL, Azure Load Balancer is involved. When I have IoT Hub talking to Event Hub, talking to Function, Azure Load Balancer is involved. That's how we're getting things around in this fabric. And it runs at an incredibly high uptime. So we wanted, again, to extend all that amazing capabilities to the customer. So then come to this diagram here, where we are using the Azure Load Balancer as an HA endpoint. Now I hope you understand why this this can be your HA endpoint, why it's okay to have what feels like a single serving of a load balancer being an okay way to distribute packets between two virtual appliances. This Azure internal load balancer rule that you've built is, in fact, it's not an appliance, it's not a single serving, it's not an inline virtual machine. It is, ladies and gentlemen, it is the fabric, okay? So there are some people that say, and understandably, for whatever reason, there are customers and partners and also even parties in Microsoft that say, you know, I'm not a big fan of the Azure load balancer. It's not the solution I'm looking for. I'm looking for something different. I want to get away from it. Well, okay, you can get away from it, but every time your virtual machine talks to its blob storage, you're using it. Every time you call Azure SQL, you're using it. Every time you put an instance level public IP on a virtual machine, guess what? You're using it, because the Azure load balancer is the route health injection, how we get, again, public addresses from that inner core out to the edge. So you can trick yourself into thinking that you're not using it, but you're still going to use it. So that's why I tend to encourage customers to think again about using the Azure load balancer, because it really is, in my opinion, a key portion of the Azure Fabric ecosystem. And we spend a tremendous amount of time and care and feeding into making it scalable, effective, and super high uptime. All right. So that's, I think, a really good discussion, because honestly, I'm not sure that anyone in Azure has had that discussion at that level with customers and partners and stuff, and I think it's good from a background perspective. Okay, so now, in our remaining half an hour, we're going to look at how we design network virtual appliances to achieve a couple of outcomes in the industry that are popular designs. So we're going to look at an active, passive, high availability NVA where we don't want NAT. We're going to look at active passive where we do want NAT. We're going to look at active active without NAT. We're going to look at active active with NAT, and then that's going to dovetail into a discussion about VM scale set and what we call scale in, and what are the pros and cons of that. Mostly pros in my mind, but we're going to talk about the differences of these architectures and what you get and what you don't, and why you might want to land on a specific one. Okay, so let's talk about active and passive with no NAT. Active and passive with no NAT, and again, this is just going to be a diagram that we're going to reuse again and again and again. Let's say that these are firewalls, really common deployment, okay? And my firewall has this concept. It has a minimum of two virtual NICs on it. It has my DMZ side, which faces public things in the internet or untrusted, and it has my internal side or trusted side. Okay, you could call it IDMZ, EDMZ. You could call it trusted, untrusted. We're very familiar with this model, and I'm assuming here that my firewalls are going to want to handle both traffic from the internet coming into a public endpoint, which is typically an Azure public load balancer 1.2.3.4, and it also wants to handle traffic from between security zones. These could be spoke VNets that I'm circling here. They could be different subnets in a VNet, but anyway, there is a private IP in Azure internal load balancer 10.1.2.4 that's providing a trusted motion from a private network segment to a private network segment. And for whatever reason, the application is such that NAT is undesirable to me. It could be that because I really need to see the real client IP on the back end for caching, for intrusion detection, for logging, for fidelity. We all know these reasons that app devs really, really want to see the true client IP. And we as networking and IT folks kind of bend over backwards to make this happen, because we want the app to function. Okay, sorry guys. Okay, so if we design this so that we eliminate NAT, let me show you what has to be done. You can understand the pro and con of this. First of all, the Azure Public Load Balancer is not something that we can use as a hop in Azure. It can't be the target of a routing table. It doesn't serve as a next hop to some other destination. It really is an internet-facing entity that's only job is to take packets from a public sphere like the internet and distribute it to a system and then deliver it to an endpoint. So if we follow what happens with the flow, let's say we have a client on the internet, Let's say this client's address is 8.9.10.11, and it makes an inbound connection request to a public load balancer. Let's just use 80, very great standard example. That's going to be forwarded to the firewall. The source address of this packet throughout this assembly will stay as the client. So if the firewall has an ACL that says, oh, okay, based on 80, or based on the destination or whatever, I'm going to send it down here to this web pool. This web pool is also going to see the source address of 8.9.10.11, right? And that's, again, for a no-NAT situation, what we want. There's a critical reason why this application needs to see that source address. Okay, fine, but that's an internet destination. Remember, in Azure, each subnet has its own default gateway, which I call the Azure Fabric Router, which is really .1 of every subnet that leads out back to the internet. And without the application of a user-defined routing table, which I always designate by the chevron icon here, the default return path for this will be out of that Azure Fabric Router itself back out to the internet. Now, as I discussed in my earlier diagram, we've anticipated this in Azure. The SDN fabric will fix up the response so that when the client sees the response, it looks like it's coming back from 1.2.3.4. We call this DSR, or direct server return. And again, it's this whole out-of-band response back around the load balancer, because that helps you tremendously with cost and capability in your load balancing tier. Well, that's all fine and dandy, but my firewall is a stateful device. I can't have the response going around it. The firewall needs the response. But if I can't change the source address to something that the firewall owns, my only other capable motion is to write a static route and point quad 0, which is the internet, back to my firewall. Now, I can use this internal load balancer as a hop. That's fine. But I'll show you the outcome of that. And remember, no NAT here. Let's say this internal load balancer, again, is 10.1.2.4. So I can write a user-defined route and say, hey, go back to my load balancer 10.1.2.4. This Azure internal load balancer will be doing health probes to these various firewalls. One of them, based on health probes, will be green because it's active. One of them will be red because it's passive. In this very simple kind of model, your user-defined route table to your Azure internal load balancer, which is a great HA endpoint for all the reasons we just discussed, will work by simple sheer luck, insofar as you only have one active game in town. The Azure load balancer only has one possible choice. Wrong color. One possible choice here. Yellow. One possible choice because the health probes tell it so. So the outcome is a stateful response to the firewall that handled the connection. So you can set up your routing table and point it to this Azure internal load balancer and have it on star, and you don't have to worry about NAT, and you get good convergence because the failover time is a factor of your health probe intervals, which can be pretty tight. You don't have to worry about a route table being rewritten, but you're stuck in a problem. You can only scale to a maximum of 2 devices, and you can only ever have one be the active device, right? So that means you're forced to what we call the scale up motion again. That means as you heat up back here for incapacity, you've got to make this skew bigger and bigger. So you've got to go from a DV2 to a DV3 to a G to an E. And so maybe you want to play that game because, again, you have this demand that you have to have the source address be in the backend application, so you take the burden of scaling up. You're just going to make this skew bigger and bigger and bigger until you satisfy. Okay, it doesn't really fit with the cloud idea of thin and wide and being able to scale out in an agile way, but this can happen. What if you want this to be active-active, though? Okay, so let's discuss this. What if these 2 firewalls are running in tandem? Well, now I have a problem, because the response that goes back to this Azure internal load balancer may, in fact, go back to the wrong firewall, because my health checks are both saying green. The Azure internal load balancer is getting this flow for the first time, and it's going to make a random kind of load balance, not a random, it's going to make a tuple-based hash load balancing decision. Well, I can no longer point my default gateway to the Azure internal load balancer anymore. I have to jettison that model. What I have to point my default route to is the IP address of one of these firewalls. So watch what's going to happen. It's all going to collapse back on itself. So let's say that this is .7. And sorry that my writing is so messy, but I'll clean this up in a minute. And this is .8. So I'm going to say go back to .7. But really, what if I want to go back to .8? How do I do that? I fall back again to where I really can't have active with the source NAT being turned off. Because if I do this, then I have to use some kind of crazy source-based routing where I say, half of the internet is going to go to .7 and half of the internet is going to go to .8, which means I'm doing crazy things to this quad zero route. I'm using wildcard masking to try to tease out one half of the internet going to one place and one half of the other. I've seen some people attempt to do this, and it kind of works, but it really is not optimal. So at the end of the day, the answer is, if you want a public load balancing motion inbound to Azure, and you simply can't tolerate NAT to change the source address to the firewall that owns the flow, you really are stuck in an active passive motion, and you're going to have to take the scale up hit. And that's not necessarily a bad answer, but that's where we are in Azure today. There's a longer conversation about why we're using the Azure Internal Load Balancer and route tables for failover mechanisms. It is part and parcel of that earlier discussion I had, which is layer 2 in an SDN fabric does not make a good global scale engine. It's all a flat layer 3 switch now. So all these great things that we had to depend upon in traditional networking, like gratuitous ARP, which allowed us to have an IP address that would float. It was called floating IP from one NIC to the other and inform a switch that this IP address is now on this port. That doesn't work in the Azure SDN fabric, because in order to expose layer 2 semantics, this whole apparatus would really have to have been a giant broadcast domain. And we've already discussed why, from a scale and cost perspective, that wasn't the right outcome. So layer 2 is not something that we can depend upon anymore. We have to retool ourselves to think about layer 3 as our security boundary, our fault boundary, and the tool set that we're going to use to design HA architectures. Okay, so that's a little bit about active-passive without NAT. Now with NAT, things get really cool. So we've discussed, let's tick this out. Okay, we've talked about that one. Now let's talk about what happens with active-passive with NAT. Okay, this is a much better thing. So again, IT professionals, we all know that NAT is like crack. It's addictive. It's not necessarily healthy for you because it disguises the real client IP and can lead to troubleshooting and ephemeral problems and ephemeral port exhaustion. But boy, is it sure easy and quick to use, and it really is this fantastic escape hatch. So for that reason, we still like to use it, and designing in Azure doesn't change that outcome. In fact, it really makes it more popular. So if I change the source IP, let's go back to our client. What was it, 1.2.3.4? Sure, we'll go green. If this comes into the Azure Public Load Balancer and is sent to this firewall, and this firewall owns that flow, and then we'll make a forwarding decision, and we'll go down, say, to this spoke to a resource down in there. If I change the IP address to that of the firewall, there's no need for this routing table, is there? That's the magic of NAT, right? Because it's not a routing decision anymore, it's locally adjacent. So if I can convince my application and dev team that it's cool to use NAT, and we can solve that visibility problem through header injection, which is a very popular trick in the load balancing industry that's been around for over a decade now. Like, for example, there's a header that's in web traffic called x-forwarded4 that will take the client address, as we know, and stick it in as a value in the HTTP header. And now my application team, although it's not ideal, can survive. They'll really see the real client address traversing through a proxy. And x-forwarded4, as we know, stacks. So if I have 5 proxies, I'll have 5 x-forwarded4 headers. And for network professionals that are doing troubleshooting, it's a little annoying. I have to get Wireshark, I have to decrypt SSL, and I have to make sure that I can see my x-forwarded4. But at the end of the day, the data I need is there. I see all of my proxies, I know the path that I took, and I can say, yes, I have a caching loop, or I don't. That kind of problem. So that's what the industry has done. NAT has been a great device to allow for simplification of routing, and then we can push client intelligence typically up into the application header and use that to survive. So that doesn't change in Azure. That means that I no longer have to worry about a route table. That means I can scale this out as far as I want, right? I can have scale in because each of these nodes will pick up its respective address and the response will simply snap back to it. Let's talk about SuperVIP for a little bit. Okay, this can be very, very helpful. If I'm into active-active, scale in, and I want this idea of a VIP, and I want to start building intelligent things for a layer 3 scale platform, I'm going to want to use in the Azure Public Load Balancer a really cool capability called floating IP. And I think you turn it on when you build your front-end IP policy. So as you know, you build a load balancer, you give it a name, and then your next step is to create a front-end IP. So as I create a front-end IP, which would be in this case my public VIP 4.5.6.7, I tick this little box in there that says floating IP. And what this will do is it will leave the destination address of the VIP in the packet intact. So that means as the packet is forwarded from the load balancer to this firewall, the destination address in the packet of the original client, let's say the client's source address is 1.2.3.4, the source address of the client and now the destination address of the original VIP will arrive in that unadulterated form, untranslated form, right here to the NIC of the backend pool member. So the Azure Load Balancer knows to deliver it, say, to .7 because that's the backend pool member address in the configuration. But the packet itself that arrives on that interface will have as a destination 4.5.6.7. We're calling it floating IP because this allows you to go ahead and reuse this concept of a VIP or a loopback or a sub interface in your virtual appliances. And it's really cool for failover. So that means that I can create each one of these virtual machines, be it a load balancer or firewall, with that same address, 4.5.6.7, 4.5.6.7. I can carry that out until the cows come home. It's scale in. I could have 100 of them. I could have 1,000 of them. And in this way, as I need to overload different services and different capabilities, so if I need 200 different public IP addresses out here to represent vanity domains, different applications, each of them requires their own A record, etc., I can carry that same thing down to here. I only need to create one private IP and one subnet, and then I get virtual overload capability. So if I have 200 floating IPs out here, I can match that here. And what's really cool is the load balancer is just going to distribute that via equal cost multipath across all these virtual machines. Now, that does mean that each one of these network virtual appliances becomes its own isolated to failure domain. But in an active scale and deployment, that's kind of what I want, meaning that if I need to maintain this, take it down for maintenance, upgrade it, or if it just simply takes an outage, that's okay because that VIP lives on again and again and again inside my 20 other load balancers. And so it's fine to take this one guy out of rotation. It's a little challenging for some vendors on config sync because their virtual IP will show up as being owned by each one. So in a layer 2 domain, that's a problem. It creates IP address conflicts. In an Azure domain, it doesn't create a problem. There's no IP address conflict. Why? Because this virtual IP that's a loopback or a subinterface or a VIP exists only in the construct of the guest OS. Azure doesn't know about it. I haven't put it in my NIC. It's not part of my subnet configuration. Azure only knows to deliver the packet to .7 and just knows to leave the destination address pristine. And then everything else that's happening is magical and amazing and inside of the brain of my guest OS, and I don't create any conflict. So people have realized that this floating IP construct is a really, really great way to get really good overload up here, match that overload down here, continue to reuse this concept of a VIP in Azure, so I can have my VIPs and so forth in my load balancers, and it gives me great active scale. So that capability can be applied to both active with no NAT and active with NAT. Okay, so let's continue to tackle those two. Okay, let me clean this up. All right, we're doing good on time. We're going to land right on time, so everyone, it's all going to be good. Okay, Let's talk about active-active no NAT. Active-active no NAT means that, again, the source address of the client needs to come through the public load balancer, come down here, and then respond this way. And as we've already discussed, active-active no NAT coming to a public endpoint is really, really problematic because there can only really be one game in town that is the recipient of a quad zero route. So either by health check or by static routing mechanism. Yep.
I think your screen is frozen because it doesn't look like it's erased. We see what you previously wrote.
Oh, thanks, guys.
We don't see the erasure. So maybe stop and restart.
You bet. Thank you, sir.
Yep.
All right, stand by. Sorry, guys. Give me 1 minute to get Skype under control here. Okay. All right, ladies and gentlemen, is that better? Do we see a clear palette of my diagram there?
We do.
Cool. Blaze, thanks. As always, thank you, sir, for the heads up.
Yep.
Okay. So active-active, unfortunately, coming through a public endpoint is not a very simple architecture today. As I've mentioned, we have to get into this idea of splitting the internet up, which is a quad zero route, means that what I'm going to do is take a wildcard mask of this. I'm going to think of all the different constituent networks that roll up into quad zero, and I'm going to set static routes for 50% of them to go to .7 and 50% of them to go to .8. It works in paper, but in reality, if I take an outage on .8, how do I converge to .7? So active-active through the public load balancer without NAT is a really, I'm not going to lie, guys, really difficult architecture. So when you're coming in from a public sphere, if you cannot have NAT today in Azure, again, the answer is you're in a scale-up motion here. It's not a bad answer. It's just the answer we have today. That means that you're going to have a set of two. You're going to be active-passive. You can go ahead and have your response to the Azure Public Load Balancer because health checking will keep this guy green and this guy red. There's only one game in town. Your responses will be symmetrical. But when you need to scale, you'll be changing your VM size and you won't be going thin and wide. So for that reason, NAT through the public load balancer is a very, very popular option, and most people will get around it through header injection as we discussed. Now, if we're talking, however, about active-active with no NAT from one private security zone to another, say spoke to spoke, or say on-prem through express route and back to spoke, things get pretty cool. Because the Azure Internal Load Balancer, which again, 10.1.2.4, listening on HA ports, will have a pool member of .7 and .8, in this case, can be used as a hop. So that means I can set routes to say that for a destination, let's just use some straw man examples, and let's say on-prem is 192.168.16. For any given destination, I want to use 10.1.2.4 as my next hop. So 10.1 would, in this VNet, would have a UDR that says for my given target, 10.2, for 10.2.16, please go to 10.1.2.4. Likewise, because routing is bidirectional, over in this spoke, this UDR needs a route that says, hey, for 10.1, for the response, the SYNAC, the UDP response, whatever it is, please go back to the same place, which is 10.1.2.4. This works. This works because in this instance, how do I explain this? As long as this Azure Internal Load Balancer is talking to the same set of NICs across these devices, and I'll get into that in a minute, the rendezvous hash is very clever. The results of the hash, which ends up being a modulus, which is a factor of how many pool members I have. So that means that if for two pool members, my modulus will either be 1 or 0, and that's the bucket the packet will go into, is going to be the same forwards as it is backwards. And I wish I had time to burst apart how a generic rendezvous hash worked to show you how the modulus comes out. I just don't have time today. But suffice it to say that the request and the response will be symmetrical through the hash and will always land on the firewall that owns the flow. So in this way, I do not need NAT because the source address is going to be handled by the routing table. Now, this is problematized. Is that a word? I just made that up. This becomes a problem in certain configurations where I'm not careful about my multi-NICs, and I'll show you. Let me expand one of these firewalls, okay? Let's say, and this is really popular for obvious reasons, that I have these two sides of my firewall. I have an external DMZ side, and I have a trusted side. And what I've done is I have an internal load balancer. And remember, for any given virtual machine, I can only ever have today one Azure internal load balancer and one Azure public load balancer. So that's the same whether you're standard or public SKU on your load balancer. But what you can do is create different front-end rules and bind those to the different back-end pool NICs. So I could have 10.2.1.4 map to this NIC, and I could create another front-end rule that represents a route for my external side for traffic, say, coming in from on-prem as opposed to through spoke to spoke. So I have differentiation in service. And I could say 10.1.1.5 as a front-end rule is going to map to this guy. Both of these could be listing on HA ports or star. Well, if I try, let's watch this. If I try to set my on-prem route coming in green and say, hey, for this spoke down here, go to this front end because I want to accept it in on my untrusted interface, sanitize it as I move through the box, and then have the response symmetrically come back to this interface and then scoot it back again, which is a really old school traditional way of understanding things through the box, where the box is metal. Each of these NICs is metal, and each of these NICs is associated with a VLAN, which is a broadcast domain. So I'm having tight segregation across my physical spaces and broadcast domains. This is a bit of an air gap here. That means that the response, typically I want it to route back to 10.2.1. Here's the problem, is that these different front-end rules can potentially declare these NICs as a different hash. So if this NIC represents bucket 0, this NIC might represent bucket 1. The more virtual machines you add to your back-end pool, the more risk you take of the hash being in a different state across these NICs. That means the response that comes back to this as a hop might land on the same firewall. It might go to this because this side 0 and this side 0. It might not. This side might be 1 on this side. This side might be 1 for that front end rule, and this side might be 0. So instead of the response coming back to the appliance I expect, it comes back to the wrong firewall. That means I have to rethink what's happening in Azure for my no NAT design. If I really don't want NAT between private segments, I'm going to have to make a decision as an administrator that my internal traffic is going to have to map to one of my two NICs. That means that for any private motion coming in, instead of it coming in on the quote-unquote front side, it's going to come around back here on the private side. Now, understandably, this drives dyed-in-the-wool firewall people like myself, 20 years doing this, bat poop crazy. It doesn't make sense from a traditional networking perspective. When I talk to firewall and security professionals about this, I do entice them to think a little bit differently about what's happening now in cloud. Remember, there's no L2 anymore. We're flat L3. Every NIC on every virtual machine by default leads everywhere. This NIC can get here and here and here and here and here. This NIC by default can get here and here and here and here and here. It's all flat. The way that I now control my network segregation in Azure is by the application of network security groups and or application security groups and routes. I have to move it up the stack. I have to move it to L3. There's no more across the box, ladies and gentlemen. This is all software. When I add a NIC on a virtual machine, I do not increase the backplane capability of that virtual machine. I do not add elegance and segregation. This NIC leads everywhere. This NIC leads everywhere. It leads to the Azure Fabric, which if I leave it in a default fail open position without my careful application of routes and network security groups, the VNet is a broadcast domain. Peered VNets extend that broadcast domain. So I'm really not other than how I'm deciding to write my static routes and policy-based routes in my firewall, from a network control segregation perspective, I'm not buying myself a lot by wanting to have packets come in one side and out the other. There's no physical cabling here anymore. This isn't even a box. It's a program running in a program running in a program. So I invite everyone to rethink a little bit that, yes, it takes a little bit more effort to think about this policy, but boy, if I can just decide I'm just going to, for internal flows, I still get this for the public. I'm not going to attack that today. But if I make this my one meeting point for internal application, I can get into cool symmetrical stuff, and I don't have NAT. So again, I invite people to think a little bit more about the one NIC model. Now, that's going to take us right here in our last 3 minutes, and it looks like, unfortunately, I don't have time for questions, but at least we made it through the material. I'll try to come off, and I can stay over a little bit if you guys want to stay over. So we've talked about active-active with no NAT. We've already implicitly talked about active-active with NAT. Remember, NAT is the Band-Aid. It's the crack. It solves everything. If you change the source address to that that the firewall owns, you don't need any routes. You can scale it till the cows come home. We've already talked about that, signed, sealed, and delivered. Now let's talk a little bit about VM scale set scale in. What I mean here is that an Azure VM scale set, which a lot of our PaaS platforms are built on, and in fact our partners, I'll just, not to pick on anyone, I'll name a few that I know about: Palo Alto, Checkpoint, Fortinet, I think F5 is coming out with this now, support their product in a VM scale set. Super, super happy to see this. VM scale sets behind the standard load balancer can scale up to 1,000 virtual machines. They can be of any particular VM type that you want, right? You control it. You get great lateral motion. You get great up and down motion by being able to resize these. You get agile scale. You get set it and forget it. You get smart, intelligent management. VM scale sets make really good bedfellows for network virtual machine tiers, I think, in my professional opinion. So it's no mistake that our Azure Firewall product is a VM scale set. We boiled it down to a single NIC because we went ahead and took the plunge and embraced this idea that in Azure there's no box anymore, there's no L2 anymore. If this is a 10 gig box, this NIC can do 10 gig, this NIC can do 10 gig. No matter how many NICs I bolt onto this virtual machine, it's still a 10 gig box. It's just now I've divided this total backplane potential up by however many NICs I add. So adding NICs doesn't buy me backplane anymore. So off of this hangs a single Azure internal load balancer and a single Azure public load balancer. And then the way that I'm dictating my security stance, so again, there's just a single NIC on this guy, is by the careful application of routes to my VM scale set. So the routes become really, really critical for me. I don't know what the heck that is. Oh, it's another meeting. No worries. Okay. These routes become my VLAN tags, guys. So if I'm a network administrator and I mess up a VLAN tag, I can cause a big outage. I'm about to get kicked out of the room. So the routes become important. So with that being said, I'm going to get kicked out of the room. I'm going to end the broadcast. I want to thank everyone for coming. This will be up on the YouTube channel. You guys have a great weekend, and I hope this was helpful. Thank you so much.